A star that was sufficiently massive and compact would have such a strong gravitational field that light could not escape. Any light emitted from the surface of the star would be dragged back by the star's gravitational attraction before it could get very far. Although we would not be able to see them because the light from them would not reach us, we would still feel their gravitational attraction. Such objects are what we now call black holes because that is what they are, black voids in space. To understand how a black hole might be formed, we first need an understanding of the life cycle of a star. A star is formed when a large amount of gas, mostly hydrogen, starts to collapse in on itself due to its gravitational attraction. As it contracts, the atoms of the gas collide with each other more and more frequently and at greater and greater speeds. The gas heats up. Eventually, the gas will be so hot that when the hydrogen atoms collide, they no longer bounce off each other, but instead merge with each other to form helium atoms. The heat released in this reaction, which is like a controlled hydrogen bomb, is what makes the stars shine. This additional heat also increases the pressure of the gas until it is sufficient to balance the gravitational attraction and the gas stops contracting. It is a bit like a balloon where there is a balance between the pressure of the air inside, which is trying to make the balloon expand, and the tension in the rubber, which is trying to make the balloon smaller. The stars will remain stable like this for a long time with the heat from the nuclear reactions balancing the gravitational attraction. Eventually, however, the star will run out of its hydrogen and other nuclear fuels. And paradoxically, the more fuel a star starts off with, the sooner it runs out. This is because the more massive the star is, the hotter it needs to be to balance its gravitational attraction. And the hotter it is, the faster it will use up its fuel. When the star runs out of fuel, it will start to cool off and so to contract. Eventually, when the star has shrunk to a certain critical radius, the gravitational field at the surface becomes so strong that the light cones are bent inward so much that the light can no longer escape. According to the theory of relativity, nothing can travel faster than light. Thus, if light cannot escape, neither can anything else. Everything is dragged back by the gravitational field. So one has a set of events, a region of space-time from which it is not possible to escape to reach a distant observer. This region is what we now call a black hole. Its boundary is called the event horizon. It coincides with the paths of the light rays that just fail to escape from the black hole. Suppose an individual, suppose an astronaut on the surface of the collapsing star sent a signal every second according to his watch to his spaceship orbiting about the star. At some time on his watch, say 11 o'clock, the star would shrink below the critical radius at which the gravitational field became so strong that the signals would no longer reach the spaceship. His companions watching from the spaceship would find the intervals between successive signals from the astronaut getting longer and longer as 11 o'clock approached. However, the effect would be very small before 10 hours 59 minutes 59 seconds. They would have to wait only very slightly more than a second between the astronauts 10 hour 59 minute 58 second signal and the one that he sent when his watch read 10 hour 59 minute 59 second. But they would have to wait forever for the 11 o'clock signal. The light waves emitted from the surface of the star between 10 hour 59 minute 59 second and 11 o'clock by the astronaut's watch would be spread out over an infinite period of time as seen from the spaceship. The time interval between the arrival of successive waves at the spaceship would get longer and longer, and so the light from the star would appear redder and redder and fainter and fainter. Eventually, the star would be so dim that it could no longer be seen from the spaceship. All that would be left would be a black hole in space. The star would, however, continue to exert the same gravitational force on the spaceship. This is because the star is still visible to spaceship, at least in principle. It is just that the light from the surface is so red-shifted by the gravitational field of the star that it cannot be seen. However, the red shift does not affect the gravitational field of the star itself. Thus, the spaceship would continue to orbit the black hole.